In this video, we will talk about one of the most important aspects of general chemistry, unit conversion and dimensional analysis. Units are a fundamental and integral part of chemistry. In general, if you write down a number without units, it is a useless value. By carefully keeping track of the units, we can easily convert from one type of concentration to another, or from one particular measurement to another. This process is called dimensional analysis. The way that it works is first you will identify your goal and write it down. You will then put down a value you think may be a good starting point. A good way to come up with a starting point is try to line up similar units. So for example, if you want volume in liters at the end, putting cubic centimeters or milliliters on top, if that's a particular ratio you have access to, would be a good starting point. You will then cancel out or convert unwanted units. Often you can use experimental conditions, either stated or implied, to get rid of unwanted units. You can also use balanced chemical equations to convert from one substance to another if needed. As you go step by step, doing your conversions, you need to evaluate your progress to make sure that you are progressing toward your end goal. One of the key components to doing dimensional analysis is conversion factors, which are sometimes based on definitions. Units in the SI system are defined in terms of the base units. We can use this to convert between related units. So definitions and whole numbers, and if the word exactly is used, can be treated as having an infinite number of significant figures. Essentially, if we're working with a definition or something that says exactly or something that can't be subdivided, it would be treated as having an infinite number of significant figures. So you don't use it when trying to determine the total numbers of significant figures for your answer. An example would be 1 inch is actually defined as being 2.54 centimeters. So if you're using this equality to do a conversion between inches and centimeters, or centimeters to inches, this would not come into play when you're trying to determine the number of significant figures of your end answer. This is to be treated as an exact definition. Similarly, 100 pennies, for example, would be $1. This is an exact definition, so this would not come into play when you're trying to work out your significant figures. 12 pieces of something is equal to 1 dozen of that object. 1 liter is defined as being 1 cubic decimeter. If we have the term exactly 5 grams, this means 5.0 to infinity grams. So it has infinite number of significant figures. It is exactly 5 grams. And so we don't take this value into account when we're trying to come up with significant figures. 3 dogs would be something that has an infinite number of significant figures. You can't subdivide a dog and still have a dog. Now, a lot of your conversion factors are only as accurate as the measurement used to define them. So, for example, converting from a joule to a food calorie, 1 joule is equal to 0.000239006 kilocalories. This is a measurement. And so your conversion, if you were to try to use this in dimensional analysis, you would only be able to write this down to a total of 6 significant figures. The value here is accurate to 6. This 1 is being used as a whole number. So this part here is your measurement, and this would be what limits your number of significant figures. Density, which is defined as the mass per unit volume, is a very common conversion factor that you will be using throughout your career in science. It essentially has the equation density is equal to your mass divided by your volume. The most common units for density are going to be grams per cubic centimeter or grams per milliliter. This itself is a type of physical property. There are 2 categories of physical properties. There are intensive physical properties and extensive physical properties. Essentially, the difference between the two is whether or not the particular property depends on how much you have or is independent of how much you have. An intensive physical property is one that is independent of the amount of substance that is being measured. Examples of this are temperature and density. Extensive properties are ones that depend on the amount that you're working with. Examples of this are mass and volume. A good way to determine which one you're working with is think about having a quantity of substance and cutting it in half. If the numerical value that you're measuring will change by cutting your substance that you're working with in half, then it is an extensive property. If it will not change, it is an intensive property. So let's say, for example, we have a glass full of water at a particular temperature. If we pour half of it out, it will still have the same temperature. It will also still have the same density. But if we take that same glass of water, full glass of water, dump half of it out, the mass of the water in the glass will have changed, and the volume of the liquid in the glass will have changed. Right? So intensive properties are ones that do not change when you cut how much you're working with in half, right? So they are independent of the amount that you're working with. Extensive properties are dependent on the amount that you're working with. The densities of solids, liquids, and gases are affected by temperature. And so when you're working with densities, it's an important thing to keep track of whether you're working at 25 degrees Celsius, 30 degrees Celsius, 40 degrees Celsius, or whatever you're working at. This could affect the density. And because density is a common conversion factor that we'll be using to go from mass to volume, it's important to keep that in mind. Let's now look at an example of how we would solve a problem using dimensional analysis. The first part of dimensional analysis is identifying your goal. So our first question, how much does 1.25 liters of mercury weigh? The density of mercury is 13.56 grams per cubic centimeter. So the first thing we do, identify our goal. So what we're trying to find is the weight of mercury. So let's put this in, let's say, kilograms of mercury. Now, we want to find a starting point that will hopefully be useful. We could either use our volume, we have one number, our volume here, and we have another possible starting point, our density. Let's actually do one, and then we'll show how you would start it with the other. So let's start first using the 1.25 liters of mercury. Okay, so we have a volume. We want to convert this into a mass. And the key aspect of dimensional analysis is using our conversions or our ratios as fractions, canceling out units, having one in the numerator up top and one in the denominator down below, and allowing those to cancel each other out. So here we would have grams on top, cubic centimeters on bottom, cubic centimeters on bottom, which is a form of volume. 1 cubic centimeter is 13.56 grams. Unfortunately, our volumes don't cancel each other out because they're in different units. So we'll need to convert from one to the other. So let's first convert centimeters into milliliters. 1 cubic centimeter is by definition 1 milliliter. So our cubic centimeters will cancel each other out, and now we're left with milliliters on bottom. Milliliters and liters don't quite cancel each other out, and so what we'll need to do is convert one of these from milliliters to liters. So we would put milliliters on top, liters on bottom. 1 liter is 1,000 milliliters. So milliliters cancel out, and our liters will actually cancel out, and so we'll be left with grams. Now to convert into kilograms, we would put grams on bottom, the unit we want to convert to on top, kilograms on top. 1 kilogram is 1,000 grams. We can now plug this into a calculator, and we would get as our answer 16.95 kilograms. In terms of significant figures, we were doing a whole series of multiplication and division, and so what we would do is look through our values to look to see the number of significant figures, not decimal places. So because we're doing multiplication division, it's whatever value has the least number of significant figures will define the number of significant figures of our end answer. So our first value here, this had 3 sig figs. This value here is a measurement. It has 4 sig figs. The one on the bottom is not part of the measurement. It's essentially 1 cubic centimeter has a measured amount of 13.56, and so the thing that has the significant figures is the number 13.56. This here is a definition, so is this, and so is this. So the last 3 do not come into play when you're trying to figure out the number of significant figures for your end answer. The value that has the least is the first one that has 3. So our end answer will have 3 significant figures, and so we would have 17.0 kilograms of mercury. Now we could have also used the 13.56. So let's say we're again trying to find our value in kilograms. But this time, instead of starting out with the volume, we start out with the density. If we're doing that, we would want to set it up such that our units line up. We have grams here, and so I'm going to write this out with the grams on top because grams and kilograms are both units of mass. So I'd start out with 13.56 grams per 1 centimeter cubed. Okay, I have grams and I want kilograms. So I would take this, convert my grams into kilograms. So I put kilograms on top, grams on bottom. 1 kilogram is 1,000 grams. Okay, so I now have kilograms per cubic centimeter, but I just want kilograms. So I'd now take this and multiply it by my volume, 1.25 liters. I put that on top because cubic centimeters is a form of volume. And so by having one volume on the denominator and one in the numerator, they will eventually cancel out if we can convert them into the same units. Okay, so I would now take perhaps my centimeters, convert those into milliliters. 1 cubic centimeter is 1 milliliter. My cubic centimeters cancel each other out. Then I would do a conversion of milliliters into liters. So milliliters go on top, liters go on bottom. 1 liter is 1,000 milliliters. And this would give me kilograms again. And you can see that it's the exact same general setup that we had for the previous one. It's just that some of the conversions are in a different order. But we're essentially doing the exact same set of multiplications, and so we would get the same answer of 6.95. This one here is the one that limits our significant figures. And so we would again end up cutting it and rounding between the 9 and the 5, and so you would still get the exact same answer either way. So often it doesn't matter where you start when you're doing one of these calculations. The key is to start. Okay, let's look at question number 2. How many grams of glucose are in 2.5 liters of a 1.32 molar, that's moles per liter, solution of glucose? So we're again trying to find the mass, this time in grams. So that's our goal. We can have a bunch of different starting points. We have here moles per liter, this one's liters. We can use the molecular weights to convert from moles per liter into grams, and because we have the chemical formula, we can calculate the number of grams per mole here. So we should always think of moles as being a fairly easy conversion into mass for the grams. So if we line up our moles with the grams, we should be able to come up with our answer. So I'm going to do 1.32 moles per liter. That's what the capital M stands for. Multiply this. Okay, I can get rid of my liters. by putting the 2.5 liters on top. Liters cancel out. I now have moles. And then if I multiply this by the molecular weight, which is grams per mole, if I put the grams on top, the moles on bottom, then my moles will cancel out, giving me grams. So to figure out the molecular weight, we would take our chemical formula and multiply it by the mass of each one of the atoms, add them all together, and that would give us our molecular weight. So we have 6 carbon. So we would take 6 times the molecular weight of carbon plus 12 times the molecular weight of hydrogen plus 6 times the molecular weight of oxygen. So that's 6 times 12.011 plus 12 times 1.00794 plus 6 times 15.999, and those are all grams per mole. So plugging that into your calculator, you will get 180.1553 grams per mole. In terms of significant figures, we are essentially doing addition subtraction. This one has 3 decimal places. This one has a lot more than 3 values after your decimal place. This one also has 3 values after your decimal place, and so our answer would be good to 3 values after our decimal place. Okay, so plugging that in here, we would have 180.1553, marking our significant figure. In terms of our units, we're left with grams, so we can actually plug this all into our calculator and come up with our answer, which would be 594.51244. To determine the total number of significant figures, we will look at the values that we used. Everything that we've done is multiplication division. In terms of our number of significant figures, the first one has 3 sig figs, the next one has 2 significant figures, and this last one has 6 significant figures. So the least of those is the 2, and so our end answer will have 2 significant figures. So our end answer would be 590 grams. We could also write this as 5.9 times 10 to the second power of grams. Those would be our possible answers for this problem. Now you can see that we were able to do this calculation, come up with our answer without having a particular mathematical formula or a mathematical relationship available to us ahead of time. Just by looking at the units, we're able to figure out how to convert from one value to another, how to solve these mathematical problems without relying on some outside mathematical formula.